Today we're looking at Notes 8-6, Rational Root Theorem. So I want to remind you a rational number is a real number, not imaginary, that can be written as m over n, where m and n are integers, basically whole numbers. For example, all of your negative whole numbers, all of your positive whole numbers, any whole number over another whole number that's either positive or negative, no matter how big or small, and even some decimals that can be rewritten as a whole number over a whole number, like 0.25 can be rewritten as 1/4. Okay, an irrational number is also a real number, but it cannot be written as a ratio or fraction of integers or whole numbers. For example, pi, e, and square root of 2 and negative square root of 3 are irrational numbers. Okay, these numbers are, if you were to type them in your calculators, decimals that do not repeat and do not end. Okay, remember also, this is very important, the degree or highest exponent tells you the total number of solutions a polynomial has. Okay, possibilities for solutions, zeros, roots, x-intercepts. Remember, these four words mean the same thing. So you have various possibilities for solutions. You can have either real solutions or imaginary solutions. Okay, and then again, talking about real solutions, what I just talked about up here, a real solution can be either rational or irrational. So I want you to look at a couple of these examples, and then you can go back and write this down. So for example, y equals quantity x minus 1 times quantity x plus 2. If you wanted to find the roots of this equation, that should be very easy for you. You set each factor equal to 0 and solve. So that would give you x equals 1 and x equals negative 2. And a very rough sketch of this would be this parabola here. A root at positive 1 and a root at negative 2. Okay, those are both rational roots, okay, whole number roots. This here, y equals x squared minus 2, produces irrational roots. Okay, if you set this equal to 0 to solve for the roots, you get 0 equals x squared minus 2. Move the 2 to the other side. Okay, you get 2 equals x squared. Square root both sides, you get plus or minus square root of 2 equals x, which equals approximately about plus or minus 1.41. So these are irrational roots here on this parabola, about 1.5 and negative 1.5. Okay? So what makes this rational, though, is not the fact that it's whole numbers, because remember, we could have decimal answers, just not decimal answers that repeat or never repeat and never end. Okay? So I can have fractional rational roots, but they just have to be fractions that are integer over an integer. All right, just wanted to clear that up just in case. Also, you could have imaginary solutions, which look something like this. Y equals x squared plus 3. Set y equal to 0, solve. You move the 3 to the other side, it becomes negative. To get rid of the x squared, you square root both sides, so you have a square root of a negative number. Remember, when you have the square root of a negative number, that is when you pull out the I, so it makes an imaginary solution, which makes perfect sense based on this graph that moves up 3 from the origin. You can obviously see this graph has no x-intercepts, okay, which brings in the imaginary part. Okay, so sometimes a graph will have a combo of all types or just some different types. Maybe it'll have some rational, some irrational, some imaginary, some rational, some imaginary, some irrational. So I just want to show you this nice little equation that I made up here. Y equals quantity x squared minus 3 times the quantity x plus 4 times the quantity x squared plus 1. If I multiply this big old guy back together, this polynomial here has all the 3 different types of roots. The x squared minus 3 produces irrational roots because this factors, if you think about it, this is a difference of squares. Anything could be a difference of squares pretty much, because what's so cool about this, I know 3 is not a perfect square, but doesn't square root of 3 times square root of 3 equal 3? Yes, it does. So that breaks down to x plus square root of 3, x minus square root of 3. This factor here produces a rational root of x equals negative 4. This factor here, x squared plus 1, remember this is our sum of a perfect square because this factors to x plus I, x minus I. So this polynomial here has irrational roots, it has one rational root, and it has two imaginary roots. Isn't that interesting? Okay, so moving on to the theorem and how we're going to apply this in our assignment today. So the rational root theorem is found on page 368 or 369 of your book, and you can look it up. It's got a bunch of math lingo in it, mumbo jumbo type, but I'm going to show you what it says and how we use it in Algebra 2. So we're going to use the rational root theorem to determine possible rational roots, and then we're going to use technology, I'm being so nice, to find any actual rational roots, because in college, if you take college algebra, they do not let you use technology, the calculator, and we'll talk about that in a minute too. So on number 1, y equals 2x cubed minus x squared plus 2x plus 5. If I want you to find the possible and actual roots, the rational root theorem says that possible rational roots can be found by taking the factors of the constant term, that means the term that doesn't have any variables, just the plain number, and divide them by factors of the lead coefficient. So the lead coefficient, you're already familiar with that word, that's this number out in front. So what we're going to do is we're going to take all the combinations of that to find the possible rational roots. So the factors of 5 are going to be plus or minus 1 and plus or minus 5. Those are the only whole numbers that divide into 5. Over the factors of the lead coefficient, that's going to be plus or minus 1 and plus or minus 2. So the only thing that divides into 2 is 1 and 2. You're probably asking me why the plus or minus. Well, if you think about it, 2, positive 2, negative 1 times negative 2 multiplies to positive 2. So that's why for all of these, you always include the plus or minus. That's an always, so just so you know. Okay, so what we're going to do now is a bit tricky. Kind of, and then you get the hang of it. So you're going to take both of these two numbers and put them over this, and then you're also going to take both of these two numbers, put them over this. So we're going to take plus or minus 1, put it over plus or minus 1, so this over this, then this over this, and plus or minus 5 over plus or minus 1. So I already did this over this and this over this. Now I need to do this over this and this over this. So plus or minus 1 over plus or minus 2, and then plus or minus 5 over plus or minus 2. And so that is going to be the same thing as, well, I'm just going to put an equals here. 1 over 1 is 1, obviously, and 5 over 1 is 5, obviously, and then 1 over 2 is 1/2. Plus or minus 1/2, and then 5 over 2, it will be 5/2. So these right here are my possible rational roots. Plus or minus 1, plus or minus 5, plus or minus 1/2, and plus or minus 5/2. So obviously you know this is a third degree polynomial. There's no way there's 2, 4, 6, 8 roots. These are possible. To find the actual, you have two choices. In college, they make you use synthetic division with every single one of these on this polynomial to determine if the remainder is 0 or not. Because if the remainder is 0, then obviously it's a factor. If the remainder is not 0, then that's not a factor. To do synthetic division 8 times on this is going to take up a whole page, if not more. So I will kindly let you use the calculator. And how you do that is you plug in this equation into the y equals, which I've already done. I've cleared the calculator. It's all ready for me to go. And you're going to use two things. You're going to use the graph, but as you know, the graph can be deceiving. And you're going to use the table. So when I look at the graph, okay, sometimes, not always, you can tell at least one or more of the actual rational roots. So it looks to me like -1 is an actual rational root. But in order to check every single one of these, I want you to go to the table. Okay, if you go to the table and one of these is a root, what should the y value be? Hopefully you're screaming at home 0, okay? So I'm going to look at -1, 0, yay, so that is, I'm already going to write it down, x equals -1 is an actual rational root. And then I'm going to look at +1, that's not a 0. Then I'm going to look at -5, nope, definitely not. And then I'm going to look at +5, and that's definitely not. Okay, to get the 1/2 and the 5/2, you have to do some changing of your table here. So I'm going to go to second table set, and instead of independent being an auto, I'm going to hit ask. So I'm going to hit enter, and then I'm going to go back to second table. And I can type in whatever values I want here. So if I type in 1/2, it tells me the y value, which is not 0, so then I know that doesn't work. And I typed in -1/2. That didn't work. And then I type in 5/2. That didn't work. And -5/2. That also didn't work. None of the y values are 0. So the only actual rational root is x equals -1. Okay, so now let's go to the next polynomial here. Y equals x to the third minus 4x squared minus 10x minus 6. So my possibilities will be factors of this plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, okay? Divided by factors of my lead coefficient, plus or minus 1. Oh, how nice is that? So that's very easy because then all of these numbers divided by 1 are just themselves. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. That's it. Those are my only possibilities. Okay, so then plugging this in the y equals of my calculator, I get x cubed minus 4x squared minus 10x minus 6. Okay, I've plugged it into the calculator. Now I go second table, and I'm going to go back to the table set, and I'm going to start it at 0 and change it by 1 and put it back to auto. These are some settings you're going to want to remember or write down. Okay, and because these are all whole numbers, there's no reason for me to type them in. They're all whole numbers. So from -6, I'm going to look all the way from -6, see if I see any zeros here on the y side, all the way to +6, because that's my possible values, go from -6 to +6. Look at that. I don't see any zeros for y's. Let's look at the graph. I'm just curious. So when I look at the graph, yeah, I don't see any possible actual roots here, but it does look like 6. 1, 2, 3, 4, 5, 6. It looks like that's a rational root, +6. But again, when I check the table, 6 does not have a y value of 0. So you know what? It looks like it, but it's not close enough. So there are no, I'm going to put none, actual rational roots. Okay, so look at that there. All that work and nothing worked out. Okay, next one. If I look at this, okay, x equal, or y equals all this here. I need to take the factors of 50, so plus or minus 1, plus or minus 2, plus or minus 3, nope, not 3, not 4, yes 5, no 6, 10 is the next one, and then after 10, the next one after that is 25, and then after that is just 50, all over my factors of this lead here, so plus or minus 1 and plus or minus 2. So I need to take all these numbers, put them over 1. So x equals, they're all just going to stay the same, 1, 2, 5, 10, 25, and 50. But then I also need to take all these numbers and put them over 2. So 1/2, and then 2 over 2, but y'all, 2 over 2 is 1. I've already got 1 listed, no reason to list it again. And then I need to put 5/2, and then 10 over 2, but 10 over 2 is 5, and 5 is already listed, so I'm good there. And then 25/2, and then 50/2, but again, 50/2 is the same thing as 25, so I don't need to list it again. So now I'm going to have to go in the calculator and plug in every single one of these to find the actual. So what would be easiest when you have such a huge list like this is to actually go back to the table, turn it back to ask, okay, I didn't plug this in the calculator yet, and then type in every single one of those to see if any of them has a y value of 0, which I don't really have time to do because I'm running out of time. And so if you have a calculator at home, go ahead and try this.